First, we'll check from the last session when we discussed about E1, and in E1 cases there are few rearrangement uh, examples which I gave you. Let's see. For example, if you have a 1 degree carbocation, the number of alpha hydrogens will be 2 here, and it will most likely be getting rearranged to this position so that the alpha hydrogens will become 6. So now it has become a 2 degree carbocation. Okay. And in case if E1 elimination is favored, that means double bond will be formed as a product this way. Got it? So typically you will, I mean, this is the major product here. And if you notice here, this way also you're getting only same product. That means even if directly without rearrangement, if you make an E1 elimination here, you would still end up getting the same kind of product. This one. Okay. So in fact, 100% you will have only one elimination product in this case. Got it? Now, notice on the second one here, if we check out alpha hydrogens, there are 4 of them and it is at a 2 degree carbocation. And if this carbocation, by chance, if at all I try to rearrange that into the other position somewhere here, let's say, okay. So in that case, the number of alpha hydrogens will still remain 4. So if it remains 4, answer is, I mean, there will not be any rearrangement. There has to be always an increasing alpha hydrogens or increasing stability. Now, what if I say that I have the starting carbon has this way, the one which has been given here. Carbocation is present here. Alpha hydrogens would be 4 in this case. And will it undergo rearrangement? Well, let's see that. Suppose if the carbocation comes at this position now the number of alpha hydrogens will be 5. So yes, in such case the rearrangement is possible. Got it? So that is what exactly is this third case. You can notice that. So from here, alpha position coming to this particular direction, the alpha hydrogen here is 4. Here it is a 2 degree carbocation. Alpha hydrogens here is 5, also 2 degree carbocation. So yes, this is definitely possible. Now here if you notice, carbocation coming on this position here at this part, and from there if it goes towards this position here, that is the complete carbocation rearrangement. Now notice number of alpha hydrogens in this case are 2. Now here number of alpha hydrogens are 4, and now alpha hydrogens are 8. So this is a complete possible rearrangement we can notice. Now coming back to starting, what exactly is the mechanism? If you notice that here, so basically we have carbon, hydrogen, hydrogen here connected with CH2 with an empty orbital like this. And that's when H minus completely transfers to this position. That way, this CH will start gaining an empty orbital, and the H2 will start, I mean the hydrogen will start making a bonding here. Okay, so that's how it leads to the formation of carbocation at this position. This is called 1,2 hydrate shift, and you may notice that whatever we have done so far is 1,2 hydrate shift only. 1,2 hydrogen shift. Here also I did 1,2 hydrogen shift, and here also I did 1,2 hydrogen shift. Next, see the fifth one. Fifth one, if you notice, I can get onto this position. So in that case, alpha hydrogens are 2. Now here alpha hydrogens are 5. So yes, this is definitely a possibility. Thereafter, from this 2 position, if I bring it to this position here, now the number of alpha hydrogens are only becoming 3. So is this possible? Answer is no. So you might wonder, sir, what if it is here, from there will it not go to the carbocation like this? Yes, it is possible. From here to here it is possibility, because alpha hydrogen now it is becoming 8. But since this possibility is not there, you will not have any production of this carbocation at all. Therefore you have to stop the rearrangement only at this position. Okay, so remember, at each step of rearrangement there has to be a progressive increase in the carbocation stability. If isn't there, then you shouldn't do any rearrangement at all. Okay, right. The next thing is about ring expansion. This we have noticed earlier also. Ring expansion. Ring expansion normally happens if there is a three-membered ring. We can expand it to four-membered ring, four to five, five to six. Six to seven happens in a very rare case. At the same time, there is a compression that can happen. Okay, ring compression can happen. Ring compression is noticeable, especially from 4 to 3 and from 7 to 6. Okay, these are the types you will notice. Okay, let me give you one or two examples how just for the sake of revision, you would remember how the rearrangement takes place. So, for example, if you have a three-membered ring with a positive charge, of course, it is a very stable carbocation. Largely, it will exist in this form, but at the same time, to overcome the strain, chances are small amount of this you know carbon, small amount of this carbocation can break and give this into a stable, i mean some stable cyclobutyl carbocation. Okay, so this is possible. If you count the alpha hydrogens, it is one. So that might give us a feeling that why can't we simply make a hydride shift in this case. So like this, in case if at all I make a hydride shift, we are noticing that the alpha hydrogens here are 7. Okay. But is it possible? No. Even though the number of alpha hydrogens are increasing, because already strained ring, you know, with sp3 carbon, if it becomes sp2 carbon with a carbocation, it is extremely difficult to gain stability here. So this is not going to take place at all. Clear? Second case. Okay. Second case, if you have a five-membered ring, a four-membered ring like this here, this way. Okay. And then in case if you have a carbocation at this position. Okay. So now you count the number of alpha hydrogens. Alpha hydrogens are 2. This is the second case. And suppose if the carbocation is being rearranged to this position. So now the alpha hydrogens will become 4. And thereafter, from that position, if you make carbocation to this position here, you will definitely have an increase in the number of alpha hydrogens, which is 6. But this is not the route it will choose instead. Because what's happening, a three-membered ring and a four-membered ring, if they get positive charge on the carbons which are forming the cyclic carbons, that means they'll already have a strain and you are increasing the strain further. Hence, that will not happen. Instead, now here ring expansion will take place. Now, how does that ring expansion happens here? Check it out. So from here, as you break the bond on this position, correct? From here, the bond will be broken. From this carbon onwards, it will attack here, correct? And from there, you will see four-membered ring has become five-membered ring now. Okay. And if I put the numbering here, 1, 2, 3, 4, 5. So 5 carbons here. On the first position, I have a methyl. Now, as the 5 and 1 got attached, the 2 must have got a carbocation form. Okay. So if at all I have to put the numbering for them, so this is what it is. 1, 2, you know, Sorry, one is here. So one, two, three, four, five. This is how the carbocation rearrangement can take place. Now notice this one. Once you get a positive charge on a five-membered ring, across the ring you can keep rotating to get it more stable carbocation. Because here you will get alpha hydrogens as 3, while here you will get alpha hydrogens are 7. So this is where you're supposed to stop. Thereafter, you can perform elimination, addition, anything you want, but rearrangement of carbocation will stop at this position. Okay. So the first step is ring expansion, and ring expansion is also a rearrangement step. The second is, 1 to hydrate shift. This is what is happening. Clear? Even if you have a five-membered ring converting towards six-membered ring, the story is the same. So check this out. Suppose I have a five-membered ring with a carbocation at this position. So what do I do? First, I will see the number of alpha hydrogens. In this case, it is only one. And from there, I will make a hydrogen shift here, by which I'll get alpha hydrogens as 7. And thereafter, I will make a rearrangement. That means I'll break this bond, make this carbon to connect here. So therefore, it would become a six-membered ring like this. Original numberings, if you identify it is one, you know, uh, 1, 2, 3, 4, 5, 6. So you can see 1, 2, 3, 4, 5, 6. This is what it is. And now notice one thing. On one position, I have two methyl groups like this. On two position, I have two methyl groups like this, and I have two position, I have positive charge. And that positive charge can be further stabilized by making a methyl to shift here, so that the positive charge comes at this position. Because you can see that the number of alpha hydrogens in this case are only 2, and number of alpha hydrogens in this case will be equal to 3, 4, 5, 6, 6, 6 alpha hydrogens. All good, everybody? That's how the rearrangement will take place. Okay. Next thing, how does the ring compression work? Check it out. Suppose if you have a four-membered ring, and by some means there was a halogen or something by which you got a carbocation here. So this will not remain very much stable. Instead, it will break in this form. And then from here, the carbon will attack on this position. So as it breaks now, you will see a bond is formed like this. And that positive charge will start moving across this carbon here. So if I put the number of carbons originally how they are 1, 2, 3, 4. Now this will become 1, 2, 3, 4. So 3 and 1 will close the bond, and on fourth position you will get a positive charge. So this is a example of ring compression. Likely, on a similar way, you can see if by chance I have a seven-membered ring here like this, and I have a positive charge here this way, and I have two methyl groups here. This. Okay. In such case, what happens? You can notice that carbon, the bond will break onto this carbon. From this C minus, it will attack here. Okay. So if I put the numbering here, 1, 2, 3, 4, 5, 6, 7. This was the original number of carbons we had. Now, we will get this as a six-membered ring starting with 1. Now 1 and 3 got connected. So 3, 4, 5, 6, 7. This is the one. And because the 2 and 3 bond has broken, but 1 and 2 bond is still there, it will be like this with a positive charge on this position. So this is what is most likely to happen. In such cases, ring compression can take place. Okay. So I guess the ring compression cases are clear. Of course, there are more cases as we go into mechanisms and various examples. You'll get to know this. Done. Come to this.
Sir,
Yeah. Yes,
sir,
Vita.
sir, can you repeat the third case?
Yes, Vita. This third case.
Yes, sir.
In the third case, first when you have alpha hydrogen one, we shifted here by which we got seven alpha hydrogens. So because of 1,2 hydride shift, I'm sure you do get that point.
Yes, sir.
Once your positive charge comes at this position, the five membered has a chance to convert into six membered ring. So you can break here or you can break here. From this carbon, you'll get a C minus. That C minus attaches here. This C minus goes and attacks the positive charge. So there is a bond formation between these two. And if this carbon becomes C minus, this second carbon will become C plus. Okay.
Yes, sir.
And that's what is the second carbon here. You can see this carbon will become C plus now. Got it?
Yes, sir.
And now, because 6 and 1 got attached on one position, still there are two methyl groups intact. So now if you compare the number of alpha hydrogens on this position here, you will see there are only two of them. Hmm?
Okay,
So
sir.
can I get more number of alpha hydrogens? Yes, by making a methyl shift. From here, if I push a methyl, then the carbocation will start appearing at this position. Okay.
Okay, sir.
Now count the number of alpha hydrogens. There are six now. So that's the last rearrangement step. Okay.
Mhm. Thank you, sir.
See, generally for these kind of questions, you know, nowadays I told you right, the mains papers have also been yesterday also a similar type of question asked where they are emphasizing more on number of transition states. They are asking on more on number of rearrangement steps, number of rearrangements, clear, or number of intermediates before the product, intermediates, number of intermediates. So if these kind of things are asked, you should understand one thing. Wherever there is an arrow means there is a transition state, because from here to here, if there is has to be shifting done, there has to be a transition state. So in such case, you count the number of arrows: one, two, three. So these three are the transition state during the reaction. Second, number of rearrangement from here to here, right? So these two, and from here to here, these three. All three steps are rearrangement steps. So this is number of rearrangements. And second, intermediates. You know that this is also an intermediate. This is also an intermediate. So one, two, three, four. So there are four intermediates forming during the reaction. Got it? Because a carbocation can never be a starting point. Okay. And a carbocation can never be an end point. It has to either convert into an alkene, an addition reaction, a substitution reaction. Something has to happen. It cannot be left as a carbocation. Okay. So make any doubt?
No doubt, sir.
Right. Now, coming to these cases, we have emphasized this before also, that when you have a positive charge here and there are three methyls, of course, we will do a methyl shift. So like this, you can see this green one is what has been shifted here. So positive charge will be coming at this position. Similarly, if you have, you know, uh, if you have to shift here, correct? Typically, hydrogen is the highest migrating aptitude, then phenyl with electron donating groups, then phenyl with electron withdrawing groups, and then phenyl with, I mean, with no group on it. And then you have 3 degree, 2 degree, 1 degree, ethyl and methyl. In such sense, definitely phenyl is the one which is expected to shift. We'll have methyl and ethyl to me. Next, if you have an ethyl, methyl, and methyl, definitely ethyl shift is what is expected. So like this we will get this as an ethyl, methyl and methyl with positive charge. So these are the types of migrating attributes you can expect. Okay. So I'm guessing all of you have done this. If not, please do check, you know, what are all the cases we are expected to learn. Now let's get into E2 mechanism, everybody. What is the basic requirement in E2 mechanism? See, first thing is that leaving group is at alpha position. I mean, of course, there has to have a good leaving group at the alpha position. And then there must be at least one hydrogen at beta position. If there is no hydrogen, then E2 type of elimination is not observed at all. Correct? If E2 elimination has to be observed, it has to be always uh, existence of beta hydrogen. Then there must be strong basis to enable E2 mechanism. Weak basis does not usually offer E2 mechanism. Got it? So let me take one example and explain, and I would expect you to, do it simultaneously with me. So write simultaneously with this example. Check it out. I have CH3, CH, H, CH, CH3, and Cl. If I take this compound, this is a 2 chlorobutane. So when you have 2 chlorobutane, okay, you know that this position is alpha, this is beta, this is beta. And what you should notice here is E2 is a one step reaction. So that itself is the RDS. And what is happening? You are adding a base to it. So which is OH minus, for example. This OH minus will be extracting this proton from here. Simultaneously, the reaction will take place. I mean, first let me write the overall reaction. The overall reaction goes like this: CH3, CH, double bond, CH, CH3 plus HCl plus H2. This is the overall reaction. Okay. So if you have to write it step by step, take this. Now imagine OH minus attacking on this hydrogen. As it takes away H plus, the bond at the same time will break, convert into a double bond. Simultaneously, at the same time, chlorine will also relieve. And as it relieves, you will notice that it is becoming CH3, CH double bond, CH, CH3 plus HCl, sorry, plus Cl minus, plus Cl minus, plus H2. Got it? Here also it is not HCl, it is Cl minus. This is what you would get. Okay. Now, since it is a single step reaction, which means you can check out the transition state how it changes. CH, this bond is breaking, and one double bond is getting made, and Cl bond is breaking and converting into minus charge. So I can say this is gaining delta minus charge, correct? And OH already has delta minus charge. That is taking away hydrogen from here. Okay. So this becomes the transition state, everybody. And transition state usually is written like this. This is the symbol we use. Okay. This is the transition state. So I can say that stability of transition state increases rate of E2. rate of E2 mechanism. So next, check out what are the features of E2. See, like I said, it is a single step reaction. No intermediate is forming. Okay. How does the transition state looks like? Let me copy once again. So this is how the transition state looks like. Okay. So how does the rate of reactivity changes for E2 mechanism? For E2 mechanism, you will notice that if you have a 3-degree alkyl halide, Rx, it will be greater than 2-degree Rx, greater than 1-degree Rx, greater than, that's it, ethyl halide. So example, I have written it here. This is how the rate would vary. Okay. Why is that so? See, you know that E2 mechanism is in fact, any elimination is endothermic mechanism and it is one step. So that means from here it is directly going towards product. Now this is where the transition state is. Notice transition state, is it more close to the reactant or is it more close to the product? Clearly you can see it is more close to the product. So the product stability decides the transition state stability. So if you notice that, if you compare the kind of alkenes that it is making, so this will make an alkene like this will make an alkene like this will also make an alkene like this, and this will make an alkene like this. Okay. So in the first case, you can clearly make out that the number of alpha hydrogens are 6. Here we have 3. Here we have 3. Here we have 0. So based on stability, this one is more stable. And between these two, if you notice, actually they are same. But this is derived from 2-degree. This is derived from 1-degree. And earlier we already spoke that 2-degree alkyl halide is more reactive than 1-degree. So 2-degree is more reactive than 1-degree. So hence this would have more chances of uh, getting into alkene faster compared to that of this one. Okay, understood how the reactivity works? So because this alkene is more stable, the transition state with respect to that particular product will be more stable. Okay, that particular transition state will be more stable. I guess these points are clear. Now you can see that based on product, if you have to analyze the reactants, which one is more stable, product will be formed most easily. So we can say the rate of E2 will be highest, I mean lowest for A, then B, then C, then D. Likewise, even if we discuss that in terms of alkyl halides, the rate will be in a similar term D, which gives the most stable alkene compared to that of C, compared to that of B, compared to that of A. Check out example B also, same thing here. D, then C, then B, then A. This is how the rate. Between A, B, C here, C definitely will be more than B, then A. These are rate of E2 mechanism. Next, type of halides. So if you compare A, B, C, D here, what are the types of halides we can get? I mean, if you have fluorine, chlorine, bromine, iodine, definitely you will see D greater than C, greater than B, greater than A. This is called as elemental effect, if you remember. So E2 also shows elemental effect. Okay. Why is that? Carbon iodine bond breaking is more easier than carbon fluorine bond. So that's why alkene formation is much easier in iodide compared to that of fluoride. Okay. This is very Simple way of understanding A2. A2 is a one-step mechanism. You can notice the graph. The transition state stability depends upon product, which is alkene. If alkene is more stable, then transition state will also be more stable. So the rate always defines based on the product stability. So notice these cases, specific cases where we have to perform E2 mechanism. These are all the cases where we need to perform E2 mechanism. Starting with the first one, you can see I can get first define which of them are alpha and beta. Alpha, beta, and beta. So chances are I can get an alkene here. I can get an alkene here. And I'm sure you do understand that this is Hoffman product. This is Shizef product. Usually, if your reactant and product does not have any complications, their complexity of bigger charge or bigger size, anything of that sort is not there, then on simple terms, we can always say Shezef is more stable and major product. Shezef is major product. Now notice same thing here with E2. So I can get uh, this being alpha, sorry, here, this being alpha, beta, and beta. Chances are I can get, as soon as the chlorine is on, I can get a double bond here, or I can get a double bond here. Okay. Now, if you notice, this is Shazef product, this is Hoffman product. Here it has less substitution. Okay. So which one is major? Shazef is major. Next one. This is alpha. Here we have beta and beta. Unfortunately, on the left side of the beta, there is no alpha, there is no beta hydrogen. Here only beta hydrogen is there. So I can say the alkene product formation in this case will be like this, double bond and like this. So this will be 100%. Next one. Here, this is alpha, this is beta. On beta position, there is a hydrogen on both ends, but removing a hydrogen from already existing double bond is very difficult. Okay, if it is already existing a double bond, it's very difficult to get a hydrogen out of it. So therefore, here no reaction will take place. Next, last one. Same logic applies there also. If we have chlorine and we have R and R and R, in that case, no reaction. Okay, sorry, no E2 elimination. No E2. See, no E2 cases, if they can exhibit E1, then they will definitely show it. So let me put it as a note here. Okay. Okay. If E2 is not eligible, then E1 route is most often observed. So E1 route is most often observed here. Got it? If E2 is not possible. So what is the E1 route in this case here? Suppose, imagine this case, I have a ethyl, methyl here, and then there is a chlorine here reacting with a strong base like alcoholic KOH. I'll explain what exactly is this alcoholic KOH is also. In such cases, right, you know that, sorry, what do you say, chlorine is not there. My mistake. Like this, chlorine is here. Okay. So you can see there is only alpha hydrogen here, but at beta position there is no hydrogen there. So now I have CH3, CH3 and ET. In such case, even though there is a stronger base, it will only form carbocation first. And once you get carbocation, there will be rearrangement. So what will rearrange in this case? What is going to rearrange? In this case, this methyl will shift from here towards this side. So what do I get? I will get this as methyl and methyl, and then I'll have an ethyl here with a positive charge. Okay, so that makes once you get this positive charge here, thereafter elimination is possible. So now the elimination gives what all products here. So I can get one product like this with ethyl, and I can get one product with double bond and ethyl. Now this one is via Shazef and this one is via Hoffman. So please do check. In these cases, even though there is a strong base, E1 is more favorable than E2 because E2 is ineligible. I mean, we cannot make any E2 because there is no alpha hydrogen at all. Okay. Now, coming to the role of what's happening with what did I say? Yeah, what's happening with the bases? When do we say something is a strong base? See, OH minus alcoholic, NH2 minus, CH3 minus, okay, RNH minus, RC triple bond C minus, then tert butoxide, then trimethylamine, okay, and ammonia in some cases ammonia. These we always assume to be strong bases, okay, and we always try to make sure RO minus also, sorry, if only RO minus is given, and we always consider them to go more for elimination rather than substitution, you know, or most often we expect that to go for E2 elimination only. Okay, so what is this alcoholic KOH means? See, normally if I take NaOH in a liquid form and add it to an alcohol like ROH, okay, this is in a limited amount, but ROH is not. So in that case, the OH minus from here can take H plus and convert into a solution which will have RO minus Na plus H2O, H2O liquid. Now, the combination of RO minus and OH minus together will make it a strong base. Combination of OH minus and KOH, OH minus and RO minus makes it a strong base. Make it a strong base, okay? But all other cases, whatever I have written, they are generally very, very strong. Okay. Now, second thing, suppose if you have been given like this, where I have chlorine at this position, and then I'm using something like CH3O minus, CH3O minus, then chances are it will get a substitution product also, and this is major, and the elimination kind is minor. like this. This is minor. But in case if you have CH3O minus and heat, in such case you will have this double bond formation, and that will be major, while this OCH3 formation, that will be minor. That will be minor here. Why is that? You know that eliminations are always elevated by heating, and in in bases like CH3O minus or alcoholic KOH for that matter, they also require heat to increase their quantity of E2. But by chance, if at all I gave you tert-butyl, which is a very strong base, got it? Or if I give you NH2 minus, very strong base, or if I give you CH3 minus, very strong base, these type of strong bases do not require heat also. They will directly give you major product as this one. So that's what you need to remember, in which case what to perform. Okay, the cases that confuse you is the first one only, when you have CH3O minus without heat given. Without heat given, it's slightly difficult to assess it, because at one position there is a mechanism called SN2. We will be learning that. That is more favorable, but not E2. But the minute you have heat, or minute you have very strong bases like this, sorry, for that matter, H minus also, because sometimes that is also given, H minus. These are all going to be very strong bases. Clear? Next, let's talk about the regioselectivity of E2 mechanism. Just like we learned for E1 mechanism, how the regioselectivity works, the similar kind for regioselectivity for E2 will also work. Now notice, when you treat with alcoholic KOH, now this is the alpha position, while this is beta and this is beta as well. Okay. So in such case, the base which is RO minus alcoholic, okay, or sorry, OH minus alcoholic, OH minus alcoholic, that has a chance to take H plus from here, or it has a chance to take H plus from here. Got it? So you would notice both of them are happening in this case. So as the iodine goes away, you'll get a double bond on this position. And on the other side, we can have double bond on this position. Sorry, there is a double bond here. This is Shezef product. This is Hoffman product. Major product will be Shezef and minor product will be Hoffman. Okay. So one is major, the other one is minor. Now notice these things carefully. Suppose uh, why this is becoming major. Now notice that the double bond which you got here will have a hyperconjugation stability which is offered by 3 alpha hydrogens. But here we have only 2 alpha hydrogens. So that makes it more stable. So the Shezef product is more stable. So more stable means it is a better direction for transition state. And that transition state will allow this to become a major product. Okay. So have you noticed something? We are supposed to get two geometrical isomers, but one of the geometrical isomers is coming out to be major product. I told you the terminology for these kind of mechanisms. We call the mechanism is okay, regio specific. and product type is regioselective. The product type is regioselective. Okay, please do check. Just a second. Right, sorry. Check this out. Let's see the next question here. When you treat with alcoholic KOH, again there are two products possible here. This is alpha, these two are beta positions. So elimination could occur on these two positions. So pH will get a double bond here and pH will get a double bond here. So obviously this is Shazef product, this is Hoffman product, this is major, and this is minor. And here also the mechanism type is regioselective mechanism, regiospecific mechanism, and the product what you are getting is regioselective product. Okay, same way here also you would notice see the third case here. Again we have alpha hydrogen here, beta here, and beta here. Well, beta here and here are same, so we don't have to worry about that. Now if I write the product, sorry, if I write the product, I would get one product as double bond here like this, and the other product as double bond here like this. And you notice that this double bond which I made has more substitution on it, so that makes it Shazef product, and this has Hoffman product, and Shazef is major. See, in this case, in the above case and this case, you can see this one and this one, both of them are major, because in both the cases you will see resonance stability is being offered. Phenyl can help in making more resonance with the pi bond, and this new pi bond which is formed is most likely going to have a resonance with the other pi bond. So if the resonance after the product formation, resonance is helping it to get more stabilized, that means the major product will be at a much higher percentage. Okay, so here also the same logic works. The mechanism type is regiospecific and product is regioselective product. Next one, if you compare alcoholic KOH, see alpha position here, this is beta, beta, and beta. There are three types of beta in this case. So if you write the products, so first one, I can make a double bond on this side. Okay, sorry, alpha, beta, yeah. So now there is no iodine there. So I'll write it like this. This is one double bond form with one pH here. And second, I can make double bond on this position like this with phenyl here, and I can make one more alkene form with a double bond here like this with a phenyl on this case. So it's pretty evident that this is Hoffman, this is Hoffman, and this is Shezef. See, Shezef is always going to be the most substituted form. So that is the Shezef part, and that is going to be major product here. For what reason? Phenyl is helping via resonance other than the hyperconjugation. Hyperconjugation is also very high here, but phenyl is also helping it in resonance stabilization. That makes it major. And because you're getting one product as a specific major product, which means the mechanism is a regio specific and product is a regio selective product. Next, here also you can see if you have bromine and alcoholic KOH is used, so you should definitely go for elimination in such case. Next, see from here, if you compare the beta positions, beta, beta, and beta, there are three types of beta positions here. So one, I can make a double bond on this carbon, keeping an ethyl group like this. Second, I can make a double bond on this position. And third, I can make double bond here like this. Okay, this is the other product which you can have. Now here, one, two, three, four. Four substitutions are there. Here we have one, two, three substitutions. Here we have one and two substitutions. So which has to be the Shezef? This one has to be Shezef. The other two has to be the Hoffman products. And that makes this Shezef as the major product. And since you get it as a major product, this logic still works. And why do you think that is major product, everybody? Because of the number of alpha hydrogens. So you can count that as well. Alpha hydrogens in this case are only 3. Alpha hydrogens in this case are 6 plus 3, 9. Alpha hydrogens in this case are, 6 plus 1, 7. Now, 3 plus 3, 6 plus 1, 7. Here we have 2, 4, 6, 6 plus 3, 9. So which one is major? This one is major. All good. See the next one. Here we have alpha, beta, and beta. These two betas are the same. Sorry. I mean, this is beta. These are the three betas. This is alpha. So these two beta positions are same. So you can consider only one. And thereafter, if you write the product, you will notice that we can get one double bond here like this. This is one product. And if you get double bond here, this is the other product. This is Hoffman product. This is Shezef product. Or is it so? No, not necessarily. Why? Have you noticed this? One, two, three. Three substitutions here. One, two, three. Three substitutions here. So, can I judge that one is Hoffman, the other one is Shezef? No. In such case, we cannot identify them as Hoffman and Shezef products here. So, you leave it there. But if you were to figure out like which is going to be major or which is going to be minor, right? Usually, you can, in such cases, first consider the alpha hydrogens here. Now we notice the alpha hydrogens in this case are coming out to be the 7 value. Alpha hydrogens in this case are coming out to be 6. But you know what happens? Still, this one is major. Still, this one is major. This one is minor. Okay. See, if the bonds are present, if the double bond is present away from the ring, right? Not inside the ring or away from the ring, it is called exobond. Exobonds. If it is within the ring, double bond is present within the ring, it is called endo bond or endo ring formation. So if you compare an exo bond versus an endo bond, usually Okay, endo bonds endo bonds are stronger than exo bonds. All right. Of course, there is certain reason to it. We'll not get into discussion of that. But my request is wherever you see a chance of double bond getting inside the ring and outside the ring, Acha, is it valid for every cases? No. Let me put that also. Only valid for 5 and 6 membered ring. Membered ring. This logic is only valid for 5 and 6 membered ring. For 5 and 6 membered ring, the inside formation of a pi bond is most likely to be more stable than the pi bond which is forming outside. So, irrespective of number of alpha hydrogens, you should always go with that aspect. Clear? This is an exception, so please do check with this sixth case. Any doubts in the first 6 cases? Please do let me know. If you haven't written, please go through the products once and please check it out and write it down. I'll give you a minute's time. Notice, unlike in E1, we learned that most of the time it is Shezef as a major product. Even in E1 cases, we always learned that because Shezef is always going to be the product which will have more stability, we always assumed and expected Shezef to be the most stable product and major product. But is it the same in the case of E2? Answer is no. In the case of E2, there are certain cases where you'll always get Hoffman as a major product. Okay. So now we are looking into those cases where Hoffman specifically can become a major product. Got it? Now let's look into that cases. First case, the effect of the base. That is, if bulkiness of the base increases, then the percentage amount of Hoffman increases. For example, you know that there is an alpha hydrogen, uh, carbon here, which has chlorine. This is a beta position, this is a beta position. Okay. Most likely, the products what you expect in this case are these two. So, one double bond on this position, the other one double bond on this position. Definitely, if you notice, this is Shezef product, this is Hoffman product. As a product stability, it appears that Shezef is major and Hoffman is minor. But unfortunately, Hoffman can also come as major. Why and in which cases? See, normally if you have less bulky cases like methoxide, one single carbon, that is CH3O minus, methoxide, ETO minus, ethoxide. So one single carbon oxides, if you have it, then it is been observed that the Hoffman is around 35 percentage and Shezef is around 65 percentage. Normally, this is how much percentage of Shezef and Hoffman are formed, which means the Shezef is major product, and this is a very normal scenario. In such normal scenario, you'll always notice Shezef is major. But what if the base is bulkier? Okay, which type of base are bulkier? The base is like tert butoxide. Okay, clear? So tert butoxide. So wherever you have seen TBuO minus, which means we are talking about this one, tert butoxide, very bulky base. Or we can have more bulkiness around it like this, even this way. This is becoming even more bulkier. Or we can have tertiary amine, that is R3N, tertiary amine, like I have nitrogen connected, of course, nitrogen as a lone pair, but also connected with at least three methyl, ethyl, or some kind of connections like this. Then we have LDA, lithium diisopropyl amine, like this. like this with lithium plus. This also serves as a very bulky base. Correct. For such bulky bases, if you have, first of all, heat is not essential for bulky bases. Even without heat, you always expect them to go for E2 elimination. Is it possible to make E2? Yes, it is. You can remove chlorine from here, hydrogen from here, make a double bond, or remove hydrogen from here, make a double bond. So again, I'll get two products here. These are the same two products which I will get here. One is Shezef, the other one is Hoffman. But yes, this time major product is found to be Hoffman product and not Shezef product. And the percentage here is almost 70% and this is 30%. Why is that? See, what happens with the bulky bases? Because the base is extremely bulkier, it has to weigh all the way inside these carbons and try to fetch these hydrogens. Because as they move, this methyl will start repelling it. So it becomes very less likely for it to possible to take H plus away from the beta position. But if this third butyl goes all the way onto this corner, here there is not much bulkiness, so it can easily extract the proton from here or for that matter here. So these two positions are easy to be extracted. So that is a problem with the bulky bases. They cannot extract hydrogens from even a slightly bulkier side of it. That's the reason why the Hoffman is assumed to be more stable product in this case. Clear? So I have written it here. So these are all the cases of bulky bases which will give Hoffman as a major product. Second thing, what if the substrate itself is bulkier? For example, you know that substrate plus reagents will give products. Now this is the substrate. Reagent is our base in this case. So base is trying to extract hydrogen from this position, hydrogen from this position. That leads to formation of double bond here like this, or it will give you formation of double bond here like this. Okay, this is Shezef product, this is Hoffman product. And what has been noticed is that Hoffman is major product and Shezef is minor product. This is what we have noticed. Okay, in such case, what I can say here, this is only observed to be 20 percentage and this is observed to be 80 percentage. Why is that? See, although the base is small, correct? But have you noticed these three groups? This is bulky, bulky, and bulky. So all these three bulky groups present at the gamma position because this is a gamma position carbon. Now that will repel this base if base will come close to that, close to this beta hydrogen. So that's why it is less likely to happen. So if this methoxide does not come very close to this hydrogen, correct, then it cannot take it. So hence what we can say, okay, double bond can form on this position or double bond can form on this position. Okay, I mean, sorry, here or here. So which is most likely to happen? Now extracting this hydrogen is much more easier because there is no crowding as such. So Hoffman assumes to be the major product in this case. Next. The third case where Hoffman is major is an elemental effect formation. For example, if I have an halogen here and this is alpha position, so you can notice this is beta and this is beta. So two different types of beta gives you two products. This is Shezef, this is Hoffman. And now if you notice on the Hoffman side, okay, when it comes to chlorine, bromine, iodine, in all such cases, Hoffman is hardly identified as around 25 percentage and Shezef is around 75 percentage. But if it is fluorine which is leaving group, then it is exactly identified opposite. 75 percentage Hoffman and 25 percentage is Shezef. Why is this happening? See, fluorine is a very uh, weak living group. So if fluorine is a weak living group, then how does the mechanism how does this mechanism happen? Check it out. Suppose if I have this group, notice this carefully. From here, fluorine is leaving. A double bond is forming on this direction, and hydrogen is being broken by the base like this. So base is taking away hydrogen, fluorine is coming away like this. This is what is happening in the case of Shazef. I'll put this side here because this side I've written the Shazef part. Let me show you what is happening on the Hoffman side. On the Hoffman side, this hydrogen is breaking. Base is expected to take that. That will initiate the double bond formation, and fluorine has to relieve itself. This is what is the transition state. So this is a transition state for Hoffman. This is the transition state for Shazef. Hoffman transition state, Shazef transition state. Now remember this point, that because fluorine is not a good leaving group, this base as it takes away H plus, what is that we are expecting for E2 mechanism? We are expecting that as the base takes away hydrogen, simultaneously fluorine should also come out. But because it is a weaker leaving group, that means the bond is still stronger, it will not depart the carbon that easily. And unless the fluorine is not leaving, you cannot get a double bond formation, which means what happens? Temporarily, a delta negative charge starts forming on this carbon because hydrogen is left fast. Fluorine is not going away. Unless fluorine goes away, this negative charge will not become a double bond. So that's why that means there is a small delta positive charge that will accumulate on this carbon. Likewise, the same delta negative charge, sorry, not positive, delta negative charge accumulates on this carbon. So now the negative charge which is accumulating is on primary position here, it is on 2-degree position here. And if you may recall, carb anion stability, if you compare, definitely CH3 minus is more stable than 1-degree carbanion compared to 2-degree carbanion compared to 3-degree carbanion. Okay, 3-degree carbanion. So you can see, so you would have this as a 3-degree, 2-degree versus 1-degree. Because 1-degree is more stable, so this transition state is more stable than this transition state. And that's the reason why transition state 1 in this case, here let me call it as transition state 1 and this as transition state 2. So transition state 1 is more stable than transition state 2. That's the reason why fluorine will always give more favorism towards Hoffman product rather than Shazef product. Is this case clear, everybody? This type of E2 mechanism, we can call it as a delayed E2 mechanism. It is called delayed E2 mechanism. Other weak leaving groups, if you compare, other weak leaving groups, which does something like that, are Nr3 plus, okay, Nr3 plus, then we have SR2 plus, then we have PR3 plus. These kind of groups will have similar problem to that of fluoride. Okay, they are weak leaving group, so anion uh, character is favorable, and since anion character is better in Hoffman, that will be major product. Is this clear? Elemental effect, I hope all of you understood. Done with it? Notice what all things we learned. When it comes to E2, what are all the important cases? First, we always expect it is more feasible in strong bases like RO minus, uh, RO minus. Then we have tert butoxide, always E2, NH2 minus, always E2, OH minus, always E2. Sorry, not always. I mean, in certain cases, which is alcoholic. OH minus alcoholic. RNH minus, always E2. R minus E2 and H minus E2. If you notice, LDA generally gives E2. Okay. So yes, these are more or less the cases which will go for E2 mechanism. Next, if it comes to rate of reaction, you will see 3-degree alkyl halide is more favorable than 2-degree, then 1-degree, then CH3, CH2X. Okay, ethyl. Aprotic solvents are most favorable for E2 mechanism, like ethers, like ketones. Got it? DMSOs. If you remember what is DMSO, CH3S double bond O CH3. This one. And DMF, which is hydrogen with C double bond O N methyl and methyl. That is dimethyl form amide. Aprotic solvents are most favorable because see, if you have protic solvent, then the bases will react with that solvent itself. Like tert butoxide will take hydrogen from water itself and go away. So there is no reaction of the alkyl halide which will happen. So therefore, there must be aprotic solvents only. We cannot have. I mean, non-polar solvents are also fine, but polar protic solvents are definitely not feasible. Next, stable alkenes, correct? So if you have these kind of alkenes, it is most favorable. I mean, if this is what is forming, then this one, then this one, okay, then this one, and lastly, simple double bond. High temperature, definitely, as temperature increases, E2 mechanism increases. So these are the important points that we learned. Okay. Yeah, one thing we learned, that sixth one, I'll just put down. So it is regio specific and regio selective. Regio selective product formation. So these two is what we have noticed. Okay. The E2 main points I have covered it. I hope you guys understood what's happening with E2 mechanism. Right. Now, I want you to check out, whenever there is an E1 and E2 mechanism happening, correct? Especially on alcohols, how does this occur? If a carbocation is forming, what is the product formation? What you will see. Okay. I'll just show you one of them. Rest of them you should be able to manage. Check like this. First protonation will make it as OH2 plus. OH2 plus is a very good leaving group. If it is going via E2 mechanism, if at all that is being mentioned, so you will directly get this product. If it is via E1 mechanism, which means first you need to make a carbocation, leaving this water, and carbocation has to be stabilized, and thereafter you have to perform elimination. That's how you'll get this double bond. Okay. Like this, I'll just put the wording here. So in what case, what to apply? So here, E2. Now apply E1. Apply E1. Apply E1. Apply E2. Got it? And see what is the product you are getting. Lastly, if you have C, A, B, C, D, they are all sufficiently bulky enough. And if it is coming via E1, so what are all the carbocations which are forming here? First carbocation, I'm not talking about the second carbocation or thereafter rearrangement. First carbocation is like this, and one more is like this, and one more is like this. So you can see this, I'll write it as A dash, B dash, C dash, and D dash. In such case, which one appears to be more stable carbocation? B. So after B, you'll have C, and then this is primary and this is primary, correct? In such case, you check out the alpha hydrogens. Here, alpha hydrogens are 2, here alpha hydrogens are 1. So which is more reactive? D is more reactive. So therefore, first one, B greater than C greater than D greater than A with all the dash form. Sorry, now I don't need to write the dash because I'm talking about the reactivity of these. But ultimately, they are all giving major product as same. Major product in all cases is this one. So just because the product is same, that does not mean the rate will be same. Okay. So rate also depends upon what is the initial uh, alcoholic form. Okay. If the initial carbocation is more stable, it is most likely to give you uh, better rate of even mechanism. Everybody clear on this case? Yeah. I have put one more assignment where you have to go through even mechanism. All these examples will help you about even mechanism. There are 16 questions. I have taken most of them from MS Shawn only. So if you can do this here, that will be more than sufficient. Correct? Now, before going into even CV mechanism, I am supposed to explain one more part of it. Second, yeah, here. Did I write that? No. Yeah, I've not written that here. Sorry. So add one extra page, everybody. This is stereochemistry of stereochemistry of E2 mechanism. Stereochemistry of E2 mechanism. First, let me explain the bond types, how they are. Okay. For example, if you have a carbon having a bond here with chlorine on this direction, and let's say other three bonds are like this, correct? Because it is a tetrahedral formation, we usually expect like this, correct? Now, if you put this bond properly, it is actually like this, carbon having these three bonds in this triangular form here, in this trigonal planar form, and then chlorine is present here like this. Got it? Why I'm saying so? Of course, this is not exactly uh, perpendicular to this one. This is not perpendicular, but slightly bent. That's how tetrahedral will be. So now you need to notice that wherever there is a sigma bond, on the opposite direction there will always be sigma star orbital. Sigma star orbital. Sigma star orbital is empty. Whenever sigma is occupied, this is an empty orbital. Okay, keep this in mind, everybody, that this is an empty orbital. Got it? Now, whenever the electron starts coming into sigma star orbital, okay, as the electrons enter into sigma star orbital, correct, it will start forming either a pi bond, slowly convert itself into a pi bond, or it will start converting into a sigma bond. Okay? Keep this in mind as well, that as the bond keeps moving away, it will start converting into either of this bond formation. Either it will become a sigma bond or it will become a pi bond. Okay. Now let's see, when would this happen? Correct. In which case it is most likely to happen. Let's see. Suppose if you have a carbon here, and then I have uh, one more carbon connected here. Then I have a chlorine here. I have one hydrogen here. One group is going inside like this. Other is coming outside. Likely here also one group is coming outside. The other group is inside this way. Okay. Now let me establish where are the sigma star and sigma star orbitals. This is the sigma star orbital of carbon. Okay. And this is the sigma star orbital of carbon hydrogen bond. Got it? Now notice one thing. If chlorine is going from here, suppose if slowly chlorine is moving away. Okay, I'll show you with the motion here. See, if the chlorine is trying to depart, chlorine will always come with the electrons, right? So with the electrons it will leave. So these are the bonded electrons, so it is going away with the bonded electrons. As it moves away bonded electrons, correct, this will start becoming empty. As it start becoming empty, you will see that the entire orbital above and below, they will start getting positive charge. So let's say this will be gaining positive charge. As it start gaining positive charge, there is one alternative we can do. Okay, what we can do, we can pull this hydrogen away. Now you can see, we can pull this hydrogen away. As the hydrogen starts moving away from here, and if this hydrogen starts getting a positive charge, that means it is go away delta positive charge, then this particular orbital, hydrogen is spherical here like this will start having electron rich. This is electron rich, orbital. So what electron rich orbital can do, it can start supporting this orbital, correct? And as this electron starts supporting this orbital here, correct, what would happen? In case if this orbital and this orbital are starting to interact, correct, they are not on the same carbon, they are on the opposite carbon. If two orbitals which are parallel to each other and start making a interaction, what do we call it? We call it as a pi bond. So that's what I told you. Either sigma star can be, responsible to form a pi bond or a sigma bond. So only if this orbital and this orbital are parallel to each other, chances are there is a formation of pi bond, correct? And that's what we expect in E2 mechanism, isn't it? We expect that the hydrogen is left by base, chlorine is coming out as a leaving group, and then the double bond is forming, correct? So if that double bond has to form, okay, if this double bond has to form, we expect that these orbitals has to be parallel to each other, which means, now can I say something? Check it out carefully, that imagine this entire scenario is happening on a particular plane like this. Okay, this entire scenario is happening on a plane like this, correct? Now can I say that on this plane, correct, this entire thing, sorry, you can see this entire chlorine orbitals and this hydrogen orbitals, they are on that particular plane, and on that plane they are parallel to each other. Now such a plane where, the leaving group, you can see the leaving group and hydrogen, proton, both are on same plane. Both are on same plane. Second, correct? The orbital interaction happens with parallel orbitals, okay? And chlorine, hydrogen are leaving at opposite ends on the same plane, correct? They are leaving from opposite on the same plane. Such a plane, where the leaving group and hydrogen both goes on the same plane, that is called as anti-periplanar structure. You can see now the molecule is at the anti-periplanar structure, and when there is anti-periplanar structure, then only E2 is possible. Otherwise, double bond formation is not possible at all. That's why the leaving group, chlorine, and the hydrogen, which is being extracted by base, both should be on the same plane but go on the opposite direction. Okay. So we need to bring the molecule such a way, if elimination has to happen, the molecule has to rotate, it has to go through different conformations, so that in one particular conformation, chlorine and hydrogen are completely opposite to each other and they are on the same plane. Then it is possible for elimination. Let me show few cases in the uh, structural basis. For instance, if at all I have uh, sawhorse projection, chlorine is here, hydrogen is here, uh, methyl is here, ethyl is here, methyl is here, ethyl is here, like this. Okay. Now I can say that this chlorine, hydrogen, and if you notice this particular plane, they both are on the same plane, no doubt. Sorry. I can say that these are all on the same plane like this. But you notice that chlorine going, hydrogen going, both of them has to happen on the same plane. See, both cannot happen on the same plane. Why, See, base has to approach from the same plane. Chlorine has to go from the same plane. See, base is coming with electrons, chlorine is leaving with electrons. So what will happen? Electrons will repel each other. So uh, base coming and chlorine going from the same direction, if it is there, it is most likely not going to happen. That's why base has to come from the opposite direction, chlorine has to go from the opposite direction, like this. Understood? Now this particular plane where chlorine and hydrogen are still on the same plane, this is called syn periplanar. Syn periplanar. So syn periplanar does not result in E2. Does not result in E2. Got it? So as an example, if I put the sawhorse conformation in this particular direction, will the reaction happen? The answer is no. Okay. In such case, elimination will not happen. Okay. Let me show you this one. Like this I have, and then I have chlorine here, hydrogen here, methyl, phenyl, and methyl. Now, if you notice the plane here, this is the plane like this. This is that plane. Now, what is this plane? Is it syn or anti-periplanar? Now, you can clearly notice this is an anti-periplanar. Anti-periplanar. Now this definitely leads to E2 product. So that means mechanism will happen via E2 mechanism. Let me show you one more example. Suppose the Sawhorse projection only, I'll show you. Chlorine is here, hydrogen is here, phenyl, methyl, methyl, and phenyl. They are like this. Okay. Now, if you notice the plane here like this is the plane. Sorry. Hydrogen is not here. Hydrogen is here. Phenyl is here. Correct. So now notice chlorine is basically present on this plane. Correct. Chlorine is present on this plane. And hydrogen actually is present on the other plane completely like this. This is the plane on which hydrogen is present like this. So they are not on the same plane. So if a base takes away proton from here, chlorine goes away from here, these electrons are here and sigma star is here. Will it make a pi bond? Answer is no. So in this conformational form, in this chair form, can E2 elimination occur? No. So let me put that. In this conformation, in this conformational structure, A2 is not possible. Does that mean in any other conformation it is possible? Answer is yes, because when it comes to single bonds, correct, you know that there is hardly any rotational barrier. You can rotate it very easily. Because you can rotate it easily, molecule, as soon as it sees that there is a chance of elimination, it will automatically rotate itself and try to convert into an anti-periplanar structure. And once you get an anti-periplanar structure, then elimination will start happening and E2 mechanism is favorable. Now let's understand that through an example. Okay, this is an algorithm, everybody. You should learn like how I'm solving, because if you're doing it for the first time, you follow all the steps. But as you start becoming more frequent, I'll give you the shortcuts like how you can quickly identify the molecule and immediately say whether you'll get cis or trans and so. So first, let us learn the algorithm for a given molecule from the um, from the Sawhorse projection to the Fisher projection to the Hoff Newman projection and then elimination. How to make it? Okay, so let's say E2 E2 based E2 based conformational analysis. Check. First, with this example, imagine this is how the hydrogen, chlorine, phenyl, methyl, and phenyl. This is the example given. And you are making it to react with ATO minus and heat. So definitely this is an elimination kind. And that too we have to go for E2 mechanism. So what you do, the first thing is you notice that this is a conformation wherein we cannot see that they are anti-periplanar. So what do? Because they are not anti-periplanar, you make sure that they come into anti-periplanar structure. So that means this is what I should be doing, right? I need to bring, this chlorine to this position, methyl to this position, and phenyl to this position. Correct? Why is that so? Because when chlorine comes at this position, then chlorine hydrogen can become anti-periplanar to each other. So that means you have to rotate it now. So rotate it such a way. Now you will get this as hydrogen, phenyl, methyl, and on the back side, if you notice, chlorine has to come here. So I'll put this structure. Now chlorine is here, and methyl went all the way on this side, phenyl came on this side. Correct? This is how made a rotation. Okay. Now you can see hydrogen and chlorine are opposite to each other. Correct? Now you can solve it from here itself. Actually, one way without going through Fisher projection, without going through Newman projections. Here only you can solve it if horse see sawhorse projection is given. So how do you perform elimination? Check it out. If elimination is being performed, ETO minus, which means we expect the chlorine will go from here, hydrogen will go from here, because base will try to extract that. Okay. If that happens, see, if that happens, now notice what would happen. See, as hydrogen is going away, this phenyl and methyl will start coming on the same plane. They are like this. They are downwards. Now they start coming upwards. Because as they are down here like this, hydrogen is up. As the hydrogen is leaving, this phenyl and methyl groups will start coming up. And same way, this phenyl and methyl group which were up already, they will start coming down, because as the chlorine is leaving, they'll start coming down like this. So now I can say, sorry, now I can say it will convert into this kind of form where I can have this line and these two, all of them present on the same plane. Now see, these all are present on the same plane, correct? With formation of a double bond. So which means the phenyl will remain on that same position on the same plane. Methyl will be here. Phenyl will be here. And sorry, my mistake. As you compress it here. So this methyl and phenyl will be on the same side. And this methyl and phenyl will be on the same side. So you'll have methyl here and phenyl here. So what are we getting now? What did we get from here? You can clearly notice that after removal of H plus and Cl minus, what we got here is this product which is trans. So in this case, trans is major product, because it's through E2 mechanism, it will offer to go via uh, anti-periplanar elimination. Okay. Now, another way to look at it is clear. Whatever the structure that is being given, right, in any form, first convert that into a eclipsed form. Okay. So I'm writing this into an eclipsed form. Converting into eclipsed form. If you write it into an eclipsed form, so that means you can see hydrogen, and then again I have to bring this groups like this. Then you call it as eclipsed form. So let me put this hydrogen here, phenyl here, methyl here the same way. And now I rotate it like 180 degrees to make it eclipsed form. So methyl will come up, chlorine will come this side, phenyl will come this side. This is the eclipsed form after rotation. This is by rotating 180 degrees. You know that once you have an eclipsed form, you can actually convert this into a Fisher projection. For a Fisher projection to happen, you need to watch the molecule from this end and from this end, right? So now what I'm doing, I'm converting this into a Fisher projection. So on the Fisher projection, as you watch, you can have hydrogen up, you'll have methyl down, and you can see phenyl and chlorine on the left, methyl and phenyl on the right. This is the Fisher projection what we have. Got it? Clear. Now what you do, correct? You can convert this into a Newman projection. Okay. Once you get a Fisher projection, you can convert that into a Newman projection. How do I convert that into a Newman projection? I can make this as a back carbon. I can make this as a front carbon. Okay. Here F and B stands for front and back. You know that front carbon has, three groups like this. You have methyl, phenyl, and chlorine. And back carbon is always written with a circle. And you see on the circle, we have the back carbon. The back carbon has hydrogen. Here we have uh, methyl here, and then we have, what do we have on chlorine side? We have phenyl. Correct. This is the eclipsed form of Fisher Newman projection. Convert to Newman. Sorry. Once you get Newman projection, what you can do, you keep whichever direction. I mean, you can fix the chlorine and rotate the back carbon such a way hydrogen comes on the opposite direction. See, like this. Keep it like this. So chlorine, phenyl, chlorine, and methyl here, and rotate backside by 60 degrees. So as you rotate 60 degrees, hydrogen will come here, phenyl will come at this position, and methyl will come at this position. Okay. Now notice this particular Newman projection. So in this Newman projection, if you notice, in this Newman projection, you can clearly notice that chlorine and hydrogen are opposite to each other. So from here, you try to remove out chlorine, and from here, the base will remove out hydrogen. As chlorine and hydrogen both will leave away, then how does the Fisher Newman projection looks like now? Now we will have a methyl here and phenyl here, pH, and here we will have phenyl, and here we'll have methyl. Okay, this is the form we have, and that means the front carbon and the back carbon now has developed double bond on it. So now let us open it. So this is front carbon and this is back carbon. So back carbon and front carbon. This is back carbon, this is front carbon. And on the back carbon, I have methyl and phenyl like this. Okay. And on the front carbon, you can see where methyl side is, on that side we have phenyl. So I'll write it as phenyl, and here I'll write it as methyl. So again, what is the product I'm getting, everybody? So you can clearly notice that I'm getting as trans product. This is the trans product. Clear? So this is a very thorough working of how actually you need to go towards E2 elimination using all the projections. Please check it out once. If you have any doubt, you can ask me. If you recall from this structure, if at all I directly take the Fisher projection, you know that from this Fisher projection, I can bring this hydrogen either to the left or right by making even number of exchanges. Okay, so I'm making even exchanges. So even exchanges means, see, from hydrogen here, methyl here, this is exchange number one. Then hydrogen here and phenyl here, that is exchange number two. So after two exchanges, where does the hydrogen come? Hydrogen will be here, phenyl will be here, methyl will be here, chlorine is here, phenyl is here, methyl is here. Correct? This is what you will get. Now, remember, we learned this part already in the case of addition reactions. That is, if you have a cis molecule and you make an anti-addition, you will get you will get trio. If you get cis molecule and you make a syn addition, you will get erythro. And if you have a trans molecule, you make an anti-addition, you will get erythro. If you have a trans molecule, you make an syn addition, you will get trio. Now, this is what you need to derive exactly in the opposite direction. If I have a trio molecule, I am performing an anti-elimination that results in cis. If at all I have erythro, I'm performing a syn elimination. The result is cis. If at all I have uh, erythro and I perform an anti-elimination, I will get trans. If I have if at all I have trio, I perform a syn elimination, I will get trans. Now let's look into this one. What is the case we are trying to do, everybody? We are trying to make an E2 elimination. E2 elimination is an anti-elimination. That's what we learned now. So E2O minus, which is an E2 elimination, and E2 elimination is an anti-elimination. So if it is an anti-elimination, what we should look into, which is the case we should look into. See, first it is hydrogen, chlorine are on the both side, same side, which means it is an erythrokind. This is an erythrokind. And on erythrokind, if you perform an anti-elimination, what is the product I should get? I should get trans. This is what you should look into. So we should get trans. So that means we should make it as methyl. I should make it as methyl and phenyl here, double bond with phenyl and methyl here. So trans is the major product in this case. Correct? So this is what we are doing. Erythro making an anti-elimination leading to trans. Got it? Now, if the Fisher projection is given in the question, see, then you don't have to go and do all of this. But in case if you have been given the uh, Sawhorse projection, you can either convert into Fisher projection and then avoid going through all of this and then directly get these products. Or if the question is already starting from a Newman projection, then you put them into opposite direction and do this. Now you understood? Depending upon the question type. Okay, if the question type has directly given with Fisher or directly given with Newman or Sawhorse, accordingly you behave, accordingly you take it and get the answer. Got it? In certain cases, cis will be the major product. In certain cases, trans will be the major product. Got it? What if four groups are different? Okay, how do I decide, sir, whether it is cis or trans? Suppose if the same question is given, but here I have, you know, ethyl and another compound, you know, is let's say hydrogen. Correct? In such case, how do we decide, sir, what is cis and what is trans here? So you need to understand this here. Suppose if you have ETO minus and ET and this is an anti-elimination. Everything is okay and you're supposed to get trans as a product. The trans is with respect to these two. Remember that. These two should be opposite. That's the logic you need to keep it. So which means you need to check these two here first. Like this. So you know that this is erythro. That logic is clear. And now you need to notice these two groups should be opposite. That is what I meant by the trans molecule. So methyl and ethyl here with phenyl and hydrogen here. So that will become the major product. Of course, this is neither cis or trans. This is based on E and Z configuration. Okay. But the logic is this. Everyone clear? So this is about the stereochemistry of E2 mechanism. Okay. Right. So we'll stop